if you see this diagram, T2 is greater than T1 and one rod is connected and cross section area of this rod is A. Now, if T2 is greater than T1, then what will happen? Heat will flow from higher temperature to lower temperature. Reason for this one, molecular level energy will transfer like this one, and heat will always flow from high temperature to low temperature. Whatever heat will flow, so rate of heat flow, that dq by dt, that will be directly proportional to temperature difference. It means if more temperature difference will be there, more heat transfer will be there. Similarly, we can write dq by dt directly proportional to area. More area, more heat transfer. And dq by dt inversely proportional to length of the slab. It means length will be more. In that case, heat transfer rate will be less. So if I combine these three equation 1, 2 and 3, what I'll get, dq by dt is equal to k times A T2 minus T1 divided by L. And this dq by dt, we can say it's a heat current. So dq by dt is equal to k times A T2 minus T1 divided by L. So this dq by dt is rate of heat transfer, and that is also called heat current. Now, if I rearrange this equation little bit, we can also write this equation dq by dt, that will be equal to T2 minus T1 divided by L by Ka. And similarly, if I compare this equation from dq by dt is equal to V2 minus V1 divided by R. So this one is the equation of electricity, and this is the equation of a thermal conduction. And if I compare this one, so this dq by dt is rate of charge flow, and this dq by dt is rate of a heat flow. This one is rate of difference of a voltage potential. This one is difference of temperature. So this is the resistance, electric resistance, and this one will be the thermal resistance. So we got one formula for thermal resistance. R thermal is equal to L divided by Ka, and in this formula K is constant, and that K is called thermal conductivity. Thermal conductivity means more thermal conductivity is there, heat transfer will be easier, and if less thermal conductivity is there, heat transfer will be difficult. So we can write this formula properly. dq by dt is equal to T2 minus T1 divided by L by Ka. Now what is L by K? That is the thermal resistance. What is T2 by T1? Temperature difference. And dq by dt, this is the heat current. So based on this one, if I solve one numerical, in this numerical what is there, the temperature of this point is given. This point is reservoir temperature is Ts, that is higher temperature, and second point temperature is Tc, that is heat reservoir lower temperature. Now this one is connected with a rod which thermal conductivity is K2, and second end is connected with rod, that is thermal conductivity K1. Now if you see the junction of these two, there will be some temperature, and that temperature will be less than Th and more than Tc. Now if I apply this formula, dq by dt is equal to K1 into A T1 minus theta divided by L1. First case I will write L2, that is K2, and this one is L2. And same formula if I apply for second case, for this one I can write dq by dt, that will be equal to K1 into A2, this is A1 and this one is A2, that is theta minus Tc, and this is Th and this one is Tc, divided by L1. Now if I equate this equation number 1 and 2, how we can equate this one? Because whatever current is flowing from this to this, same amount current will flow from this to this one. Means current flow will be same. So whatever current will flow from first end TS to midpoint, and same current will reach from midpoint to extreme point. And temperature of this point, this layer, that is Tc. Now if I equate this equation, so we can write K2 into A2, and that is TH minus 0 divided by L2, that should be equal to K1 into A1, that is theta minus Tc, and that is Ts minus theta, not 0. So Th minus theta, and this one is theta minus Tc, this one is L1. If I solve this one, I can calculate theta, and after calculating this theta, if I put value of theta over here, I can calculate dq1 by dt. Similarly, we can calculate dq2 by dt, and that will be equal to dq by dt. So from this numerical, we calculate interface temperature and how much heat will flow. Solve one numerical based on this one. If you see this, in this one temperature of this point is 12, this point is 51, this point is 4 degrees Celsius. In this question, what they are asking, what is temperature of this junction? Let's say temperature of this junction is T. Now we know heat will flow from high temperature to low temperature, and we are assuming T is less than 12 degrees Celsius. Just we are assuming T is less than 12 degrees Celsius. If I assume T is less than 12 degrees Celsius, it means heat will flow from this to this one, and heat will also flow from this to this one, and heat will flow from this to this. Means T is less than 12, but obviously T is less than 12, and T is more than 4 degrees Celsius. Now let's say this heat is dq1 by dt, this heat is dq2 by dt, and this heat is dq3 by dt. So basically these are not heat, these are heat current. So heat current is coming towards junction from dq1 by dt, second heat current from 12 degrees to junction, that is dq by dt, and from junction to 4 degrees Celsius dq2 by dt, dq3 by dt. Now if I write equation of Kirchhoff law, so dq1 by dt plus dq2 by dt, that should be equal to dq3 by dt. And all rods are similar, their thermal conductivity also same. So what I can write, first case K into A, that is 51 minus T divided by L. In second case I can write K into A, that is 12 minus T divided by L, and in third case what I can write, K into A, that is T minus 4, higher minus lower, divided by L. And if I solve this equation, finally what I'll get, 51 minus T plus 12 minus T is equal to T minus 4. Now T we can take one side, so that is 51 plus 12 plus 4, that is equal to 3T. And if I solve this one, 51 plus 12, that will be 63, plus 4, that will be 67. So T will be equal to 67 divided by 3. That's how we calculate junction temperature. Now after calculating junction temperature, if you want to calculate dq1 by dt, so dq1 by dt is equal to Ka, and that is 51 minus T divided by L. Everything else is given, K is given, A is given, 51 is number, and T is temperature, that's already we calculated, and L is given. So we can calculate how much heat current will flow, and we can also calculate what will be the temperature of the junction. Alright, now there is another numerical based on this one. In this numerical, temperature of this point temperature is 100 degrees Celsius, and this point temperature is 0 degrees Celsius, and diameter is same, and length of this one is, copper length is 75 centimeter, and steel length is 125 centimeter, and copper thermal conductivity is given and steel thermal conductivity also given. What they are asking for? They are asking for what will be temperature at this question mark. Means what will be temperature at this one? Let's say temperature at this one is T. Now whatever heat will flow from this point to this one, same amount of heat will whatever heat will flow from this to this one, same amount of heat will flow from midpoint to lower temperature. So I will find out heat flow from 100 to T, then heat flow from T to 0, and then what I will do, I will equate these two equations. Now if I find out dq1 by dt, so dq1 divided by dt, that should be equal to K copper into area of copper, that is equal, that is 100 minus T divided by length of copper, that is 75 centimeter, let it be 0.75 meter. Now if I calculate dq2 by dt for second case, if I am calculating dq2 by dt, means heat flowing from junction to this point, that we can write K steel into area into, that is T minus 0 divided by length of this one, that is 1.25 centimeter, 1.25 meter. And I need to equate equation number 1 by equation number 2. Why? Because whatever amount of heat will flow from this to this one, same amount heat will flow from junction to that. Now after equating these two, and I will substitute value of everything, in that case what we'll get, after substituting the value of everything, what we'll get, area and ks, and we will get T is equal to, just I am equating these two, K into cu into area, that is equal to 100 minus T, that should be equal to ks into area, and that is T minus 0, and this one is how much, 0.75, and this one is 1.25. A and A get cancelled, we cancel these two, and after that if I calculate temperature, that temperature will be equal to 93.3 degrees Celsius. After getting temperature, just I substitute value of temperature either in first one or else in second one, and I will find out how much rate of heat flow will be there or heat current will be there. And by the way, TQ1 by T2 will be equal to TQ2 by dt. TQ1 by dt, that should be equal to TQ2 by dt, because rate of charge flow, rate of current flow, not charge flow, rate of current flow will remain same. That's what principle we are using, that is Kirchhoff law. Whatever incoming current will be there, heat current I am talking about, same amount of outgoing current will be also there. Now this formula we are applying where area is constant, and if area is not constant, in that case this formula is not applicable. Which formula I am talking about? dq by dt is equal to K into A T1 minus T2 divided by L. This formula we can simplify away. dq by dt we can write, that is equal to T2 minus T1, T1 minus T2 or T2 minus T1, same thing, higher temperature minus lower temperature we keep. So here we can write this formula. Now L by K is thermal resistance. L by K is called thermal resistance. We already explained this one. And in thermal resistance, what happens? How to calculate? Length divided by K divided by area. So first let's say calculate thermal resistance of this diagram. If you see this diagram here, I am selecting one strip, and this strip thickness is dr. Thickness of this strip is dr. So lower side temperature and upper side temperature, means this temperature and outside temperature, there will be difference in that temperature. And if I calculate this R will be equal to integration dr, and integration dr will be equal to dx, that is length, means RTH is equal to what? L divided by Ka. So first I will write length, then K, then area. So dx is the length of that. Length of what? Length of this strip, that is dx. So dx is the length of this one, and temperature difference of this one will be x, and divided by L, K into A. And what's the value of K? That is K only, and A will be equal to 4 pi x square. because radius of this one is x, so we can say area of this one will be 4 pi into x square. So what I did, in place of L I am writing dx, in place of k I am writing k, and in place of a area I am writing 4 pi x square because it's a hollow sphere. So if I calculate this whole thing after integration, I'd integrate this one from a to b. Lower area, lower radius of this one is a, I am taking a, and upper radius of this one I am taking b. So upper part of, and I will get b minus a divided by 4 pi into KAB. After integrating, I got this one. Now directly I will use formula dq by dt, that should be equal to T2 minus T1 divided by R, that R is thermal resistance and R value is given. So if I solve this R value and substitute R value over here, so what I'll get 4 pi KAB, that is T1 minus T2, T1 minus T2 or T2 minus T1 depend on temperature, higher temperature minus lower temperature, that is B minus A, heat always from high temperature to low temperature. So from this one we can find out dq by dt. So this is the dq by dt, and dq by dt is what? Heat current. So heat current in this case we can find out using this formula. In a lake, what happens? It freezes layer by layer. So first layer, then second layer, then third layer, and that layer is very small. So at time you notice that one, and if freezing is happening, outside temperature should be negative, then only freezing will happen, and inside temperature continuously keep on decreasing. So it will freeze layer by layer. The moment you notice, in that case what happened, this much layer is already freezed and that distance is y. Now next layer is freezing, that layer is dy. So what I am saying, in at a y distance I am taking layer of ice, that is dy. So if you see how much heat is supplied, that heat supplied is equal to, we can write k into A into T1 minus T2 divided by D into T, that is dq by dt formula, simply dq by dt formula only. Now if this one I can also write q is equal to m into O minus T divided by y into T. Dt, time is dt, for dt time I am talking about. Similarly, you can also write this q is equal to m into L, and m is equal to mass. So mass of this one is equal to volume into density. So I need to calculate volume of this strip. So what will be volume of this strip? Area into length, volume into density. This is mass and dy is the length. So this is the q. So if I compare this first q and this second q, so if I compare these two things, so finally what I will get, Ka T dt divided by y, that should be equal to a rho L dx. And if I separate this thing, not dx, that will be dy. Now if I separate this thing, so what I'll get, dt, that will be equal to, dt will be equal to rho L divided by k into t, and that is y dy. And if I integrate this one, let's say we are integrating this one from y1 to y2, so final formula, time taken to freeze, that will be equal to rho L divided by 2kt, that is y2 square minus y1 square. So this is formula used